Okay, so a brief tutorial. There's a thing people do at best man speeches. They turn up with a large pile of paper and say, I've got a short speech. I've got a million slides, but we'll get through them quickly. What I want you to take away from this is a high-level overview of some new technology being discussed in the IETF, but it's really an old technology as well. What you should not expect is to understand too much of the details, all of the possible applications of this, and this is not a sales pitch for the technology or for the vendor I happen to work for. It's meant to be an education. So, some background on traffic engineering. Hopefully you have a bit of clue. The purpose of traffic engineering is to control how packets or data flow through a network to get the best possible service and the best possible use of the network, maybe to avoid bottlenecks or suspect resources. So we have two tools in traffic engineering. One of them is strict paths. A strict path says this is exactly the route through the network your data will follow. And there are two approaches historically to this. One is to put the information in the packet header, and we see that in the strict source route option in IPv4, but not much used. And the alternative approach is to put the information in the network and then attach a label or a flavor to the packet so the packet follows that information. And we see that in RSVP-TE, in an MPLS network. The alternative to a strict path is a loose path. And there what you're saying is, I want you to follow some, to pass through some hops, and how you get between those is up to you. So you chop the path up into segments, and you can still use either the packet header with a loose source routing option, which shows up in IPv4 and IPv6. And then the network is required to have enough state in it to get the packet between those hops. So what segment routing is doing is applying those old techniques in a slightly new way. So the path information gets placed in the packet header. So every packet contains enough information to direct it through the network. No control plane or signaling state needed. And this idea first turned up in the IETF in 2013, so we're 4 years in the process here. And I was part of chartering a working group to look at this in October. And there are now about 500 people on the mailing list looking at it. But very slow progress, only one RFC to date, and that's just a problem statement. The level of interest is high, with 50 or so internet drafts at various stages of progress, and all of the big vendors are playing. So objectives are pretty much the TE objectives. But we're trying to leverage the shortest path forwarding, so to benefit from what the IGPs are doing, and then periodically or for specific points, steer the traffic away from the shortest path to either load balance or create protection paths or repair after failure. We want to do this without putting complexity into the network, so removing the signaling protocols and trying to reuse the forwarding paradigms, either IP or MPLS, and to reuse the existing routing protocols. Okay, so that's background. Now moving into details a little bit, there are 4 key terms. The segment routing domain is simply a collection of routers that can do segment routing, and unsurprisingly, ingress, transit, and egress. And what might a domain be in reality? It's probably an IGP domain, so an area. An SR path is a path through the network that is different or potentially different from the least cost path. And it's built up out of segments, where a segment is that piece of path that connects 2 points in the SR domain. And it may be just a single hop between adjacent routers, or it could be a multi-hop piece of path. And we represent each segment with a segment identifier, which has either a node local or a domain-wide significance. And we'll see the importance of the 2 things in a minute. So there's a picture of exactly that. You see the end-to-end SR path. You see what is obviously the IGP shortest path. And we've got 3 blue segments there taking the traffic off that shortest path and home to the egress. So those segments, or the segment identifiers, have a number of different possibilities. We can identify an adjacency, so essentially an interface, a single hop. Or we can identify a prefix, and a prefix is going to be 1 or multiple hops, and you get there by following the IGP shortest path to that prefix. And then we can have an anycast segment, which is really a choice. It's an identifier that identifies a number of different prefixes, and you choose which one you're going to based on ECMP, load balancing, whatever. And then there's a final type of identifier which is really useful. It's a binding SID, and it allows you to represent a tunnel or another path. So now we can actually have in our address instructions go from this hop to this hop, and then go down, dive down this tunnel. So how does it work? The segments define the type of path, as I say, some a single hop, some multi-hop. We build a segment routing header which we insert into each packet, and that header is a list of each segment identified by the segment identifier that the packet is required to traverse. So that's not necessarily every node it has to traverse. These are loose hops. And then the network has to contain enough information to resolve getting the packet from one end of a segment to the next. And what we've done is said, the IGP pretty much does this for us already, so we can really leverage it. Or we can install this information some other way, which may be an SDN type of approach, and some people have enhanced BGP as well to achieve that for us. And then we have to look at, well, how does this show up in the forwarding plane? We're putting the segment routing header into the packets, so we need to be able to do this in MPLS. And in MPLS, the segment routing header is simply an MPLS label stack, where each label in the stack represents a segment identifier. And we need to be able to do it in IPv6. And the approach there is to define a new routing extension header and fill that with a list of IPv6 addresses where each address is a segment identifier. And then the third approach is to build the MPLS segment routing label stack and encapsulate over UDP. And that allows us to route this through an IPv6 or an IPv4 network. So some examples. For MPLS, the SIDs are not labels, okay? A segment identifier is not a label, but we encode it and carry it in a label. And it's a slightly subtle distinction, but the important point there is that some of the SIDs have domain-wide significance, and we need to map them as we go across the domain, depending on how the different routers in the domain allocate their labels. So there has to be a way of allocating those SIDs and coordinating them across the domain for the node-wide significance. Each node in that approach reserves a block of labels that will be used for segment routing, and that's called the sRGB, and the IGP advertises that, and then we can say each segment identifier is an offset into that block of labels. It's a little bit complicated, but it handles the fact that some routers can only allocate from one part of a label space and some routers from a different part, and the two just sort of don't go together unless we do this approach. So here's a worked example with a trivial network and adjacency segments. So we're just going to do a hop by hop. It's like a strict explicit route. And I wonder if that shows up. Yeah, sort of. The comforting thing is that you can read it and I can't. So the router, R1, advertises a local label that says, when I see this label, I'm going to send out of a link a specific link. So if a packet arrives with this label, it tells me what link to send it out of. And so all of the routers do this. And now, from R1 to R4, I can send a packet with a big stack of labels on the top. The top one, 82, when it's received at R2, it tells R2, okay, what I do is send this packet onto the link to R3. And at the same time, I pop the label. So this is a pop and go paradigm in MPLS. And then 8.3 is revealed, so R3 knows which interface to send that out of, and so on round the network until R5 pops the last label, looks it up, and says, oh, that's going out of the interface to R4, and that's just raw payload. So working backwards, at R1, when R1 wants to send a packet to R4, along this path, it can build that label stack, it computes that label stack, pushes it onto the packet, injects the packet, and off it goes as pop and forward all the way through the network. Also got a simple example for using the prefix segment. We're trying to get a packet from R1 to R7, and we can see the shortest path there with the green arrows. So each node advertises its sRGB base value. This is the block of labels that will be used, and you see those are different values across the network. And R7 also says, look, if you want to reach the prefix for me, my offset is 7. So that gets propagated through the IGP. And R1 now knows, if I want to send the packet, I'm going to send it to R2, that's along the shortest path, and I'm going to attach to it the offset 7 and R2's block 100. And R2 will do a label swap. It says, okay, it wasn't for me. It's going off to 7. I know where that is on the shortest path. It's going out to R3. R3's block is 500. I put in the offset 7, and it goes. R3 says, oh, I'm adjacent to the destination. I pop the label and go. And we can do the same thing from R4. I've also got an example for a more complicated prefix segment example. I'll skip that as an exercise for the reader. It's in the slides. So IPv6, how that works. There are two modes being discussed at the moment. One is encapsulating mode, and one is simplified mode. The encapsulating mode says take the IPv6 packet you've got and wrap it up IP in IP, and then do the segment routing on the outer header. And the simplified mode says take the IPv6 packet and insert the extension header into that packet as it is. Amusingly, all the standards work at the moment strongly advises on using the encapsulating mode, and all of the prototypes that the vendors have built so far do the simplified mode. Simplified, I guess, because it's simpler to implement, but it's really ugly to diagnose, in my opinion. And I think the reason that the standards say do the encapsulating mode is not just because the IPv6 freaks are throwing their weight around. It's a more sensible approach. Anyway, in both cases, the extension header carries a stack of SIDs. So the example I've got is for the encapsulating mode, and we come in at the top with a nice TCP/IP packet, and that gets pushed down to the bottom because we're encapsulating and putting a new IP header on top and a segment routing extension header. And what you see in this is that the next header field says there's a segment routing header coming, and the source and destination addresses have got munged. The source is where we entered the domain, and the destination address is the next segment address. So that's pulled out of the segment stack that's there. And then the next node we go through is not doing segment routing, it's just an ordinary IP forwarding towards that destination address. So nothing much happens apart from the hop limit changing, and then we arrive at :3, who says, oh, I'm the destination of this packet, so I need to look at it. I discover that there's a segment routing header present, and so I'm going to go and look through that segment ID stack and find the next destination to forward onto, and we change. The source address remains the edge of the domain where we came in, but the destination address now changes to the new segment endpoint, which is the :4. And on we go with a normal routing step until we reach :4, who will look at it and discover I'm the last segment in the list, so I'm the endpoint, so I can strip off the encapsulating header and come back to the payload header, tweak the hop limit, and send the packet on to its real destination. There are two advanced types of segment identifier I want to cover. The Anycast SID. The Anycast SID turns out to be really helpful for getting you past failure points, getting you past bottlenecks, and for load balancing. And what you do is put in a segment identifier that identifies a choice of next hops. And they can be multiple hops away, or they can be adjacent. and this allows you to build quite a robust network, and certainly operators that I'm talking to about segment routing are really interested in using the Anycast SID as a way of building resilient and reliable paths through a traffic engineering network. The other advanced use I wanted to mention was the binding SID, which is identifying a tunnel. Do we have a picture there? No, we don't. And here, the tunnel could be another segment routing path, or it could be some other technology tunnel, maybe something set up with RSVP. Maybe you're actually exiting the IP MPLS network and going down some other technology tunnel, and you can assign a SID to it to direct the traffic that way. So SRv6 is really interesting, and it's pretty powerful, but it's got some issues, I think. One of them is that the header can get quite large, and that may impact on MTU, and actually it impacts on some existing silicon. There's also some argument about the standardization around SRv6, as I mentioned before, whether you encapsulate or use the simplified approach. And additionally, there's a concern about whether you have MPLS and SRv6, how you trade between them, and whether you pay to have both developed and maintained. So there's an option we've been working on fairly recently to carry MPLS SR over UDP with the objective of doing everything you can do in segment routing and getting segment routing in MPLS and IPv6 networks, tunneling over IPv6 or embedding in IPv6, and arriving at only one forwarding paradigm for silicon. So the approach here is really to leverage RFC 7510, which is MPLS over UDP, which is fairly widely implemented and deployed a fair bit. And what we're doing is just saying, you can already do this. All you do is take MPLS SR, package it up in IP UDP, and send it to the next segment routing router to the end of the segment, where you will drop off the IP UDP, do the MPLS SR, package it up, and send it again. So the IGP processing is just like MPLS SR. The source node is just like MPLS SR, but then it wraps it up in UDP and IP and sends it to the destination identified by the first SID, and then on you go. Control plane I'm going to run through really fast, except to say IGP, okay? IGP advertises prefixes and interfaces. All we have to do is advertise the SIDs along with them, and it's really simple to do. And then somebody has to compute paths. That's fine. You can do that in a central controller, or you can do it at the head end. And if you use a central controller, well, it's SDN, so beware. You have single point of failure, maybe. You have security risks. You have potential performance bottleneck. But you have the global visibility. And one thing about segment routing traffic engineering is it does not reserve resources in the network. So if you have concern to reserve bandwidth, you need somebody central monitoring that. And then, of course, you need a southbound protocol to handle that. So some use cases. This is a step-by-step PCE with segment routing, what's going on is you request a service to a controller, the controller computes a path through the network, tells the head end what stack of SIDs to apply, and when the traffic comes in, it's classified against that, the SID stack's imposed, and the packet is forwarded through the network. That's fairly simple, straightforward approach. The data center turns out to be a popular place for segment routing to be discussed, and extensions to BGP have been proposed as a way of pushing instructions, forwarding instructions related to segment identifiers down into the data center. And you build a stack of labels that basically say, this is the egress top of rack, this is the egress server, this is the egress VM, and then the payload. And now you can leverage those identifiers to move through the network and pop and go when you reach each one. An interesting thing develops that if you want to do end-to-end routing, you really would like to be able to see a path right the way across maybe multi-homed networks. And so assign binding SIDs to tunnels across those networks and discover how the end sites are homed. And rather than just have BGP picking BGP's best path, you need to allow those multi-homed access gateways to be advertised right the way through so that you can see them end-to-end and choose a path. Turns out to be a couple of almost trivial extensions to BGP to do this, and there's a couple of drafts out there explaining how that can all be put together almost for free. And then two use cases for the UDP tunneling. The first is the simple attachment of two SR domains across an IP core. That's just like MPLS in UDP. So it's a tunnel which carries the whole MPLS SR stack right the way across the network. The other approach is slightly more complicated, and this is the mixed mode. So you can have nodes that are legacy nodes and simply don't understand segment routing. And you can have nodes that do understand segment routing and they're on the path, but they don't actually have to do anything more than IP forward the packet. And then you have the segment routing nodes, which are the places to which you're steering the traffic. So the tunnels run between the dark blue nodes, and the other nodes are just doing IP forwarding. And I didn't see my 2-minute warning, so I'm doing well. Segment routing then, okay, what it's trying to do is achieve traffic engineering, but move the state from the network into the packets. So we're removing some of the complexity from the network, simplifying the protocols that you have to run, but the cost of that is that you have to put some complexity into a controller and you have to put some information in packets. There are a number of problems still not properly addressed. Some of this is fast reroute. What happens when there's a failure in the network? Can we do loop-free protection? A big open issue is OAM, and there's some work started on OAM for segment routing, but it bothers the hell out of me that we've got this far, 4 years down the line, and people are only starting to talk about how might you operate this in your network. Inevitably, optimizations on these proposals will come along. It's inconceivable that we've got it right first time. and we have zero operational experience. We really don't know how this is going to perform in live networks. And I guess that's where operators come in. So please talk to us. Please set up labs, play with it, and then ask questions. Or don't ask questions.
Hello, Tom Hill from Bytemark. I was curious, a conversation came up probably a couple of years ago when segment routing was first sort of being talked about how Martini Draft EOMPLS targeted LDP tunnels could coexist with SR, or whether or not there was going to be a solution for that baked into SR somewhere along the line for replacing those services to avoid having to use targeted LDP and segment routing alongside each other, or whether or not that's just perfectly reasonable and that's what we should do.
Right, everything is possible. So I talked about segment routing replacing RSVP, but it also replaces LDP. Can you run them in parallel, ships in the night? Definitely. Can you run them one running over the other? So part of the path is LDP and part of the path is segment routing. Yes, you can do that, and there is a discussion out there in a draft on coexistence for that. Personally, I think I would try to make a decision as to which direction my network is going in and migrate ships in the night towards that as a final position.
I think I agree. I would prefer to be running segment routing instead of LDP learning across my IGP, but I'm still unsure if what I can do with E-line services, so Ethernet over MPLS, pseudo-wire tunnels. There doesn't seem to be a solution for that in segment routing, and it looks like we will still be relying on targeted LDP for that.
I think you need to run some coordination between the edge points, if you like, between the access circuits, so that the destination knows what's coming out the wire at it. Whether that coordination is an SDN approach or whether it uses signaling is horses for courses. But because there's no signaling in segment routing, the alternative would be that each packet identified its payload and encoding type and so on, and that gets, I think, ugly.
Indeed. Thank you.
Hi, I think you covered the issue of header insertion very eloquently there. People in the room might not understand quite the amount of angst and pain the IETF went through in that discussion about whether it should be allowed. Obviously, IPv6 is now advanced to internet standard as RFC 8200 saying thou shalt not insert headers. But as you say, a lot of the vendors are doing just that. How do you think that's going to shake out? Are the vendors likely to move to encapsulation, or do you think they'll do what they want to anyway? I'd be interested to hear your view.
Well, vendor hat firmly on, the vendors will do what they're bloody well told. And they will be told by their customers. Now, that might come as a surprise to the operators in the room, but it's amazing what an incentive a check with a large number of zeros on it has. I think that the reason why the simplified mode was done was because that was what was hacked together in the first implementation, and people doing other experimental implementations wanted to interoperate. Where we end up, I really couldn't guess, except, of course, personally, so vendor hat off, I'm an MPLS person, so why would you want to do SRv6?
Okay, no more questions for Adrian? Okay, thank you, Adrian.